We're going to talk about an application of second-order linear differential equations, and this is the prototypical example, something called a mass spring system. Imagine you've got a spring with a mass at the end of it hanging from a ceiling. Now, springs on their own, they have a natural length. So the natural length of the spring is some value L, and the reason that's important is because anytime you put a force on a spring, it reacts in a manner that's opposite to what you apply. And that's really going to be the driver here in all of the motion that's going to occur. So in this situation, let's just say the spring and the mass are hanging from rest. So at rest, that means the acceleration is 0 and there's no motion, right? There's no change in velocity. Everything is staying put. Now, we've got Newton's law. F net says that's equal to mass times acceleration. So if we talk about this, the situation that's happening here is that we've got the natural length of the spring, and then when we put the mass at the end of it, it extends it some distance L beyond. Now, if we talk about a free body diagram for the mass, we've got the force mg being pulled down, and there's a force due to the spring that gets pulled back up. So the spring is something, the restorative force is called Hooke's law, and it's always negative k times something x, and this is the distance beyond natural length. So in our case, the distance beyond natural length here is going to be L. So we'll have negative KL coming back up. Now, at rest, as we said, the acceleration is 0. If we take downward to be positive, that means we'll have mg minus KL, and we could relate that additional length to the parameters of this problem. We are going to consider what happens when this system is in motion. Now, to be in motion, we have to, again, discuss what's happening with a natural length of the spring, this additional length that the mass pulls it down, and we're going to set that to be our reference point. We'll say that that's y of t equals 0. Now, y of t will be the of the mass relative to this equilibrium point. And so what I mean by that is, if you decide to pull the mass down even further and then let it go, you could imagine that the mass is going to start bouncing up and down, and it's going to bounce up and down relative to that equilibrium position. Now, at any given time, you can add this additional distance to it, this y of t. Now, we are also going to assume that there's air resistance. And the air resistance is proportional to the velocity. And so we're going to start putting this all together. If we talk about a free body diagram, once again, assuming down is positive, we've got the mass, force due to gravity, is mg going down. And then we're going to have two forces in the opposite direction. Number one, we're going to have the spring force, and this is going to be negative k times L plus y. And it's L plus y because the natural length is little l, and then L plus y at any time is the distance beyond that. And we're also going to have this cy prime. This is the air resistance force that is going proportional to the velocity. So according to Newton's law, F net equals ma. The net force will be mg minus k into big L plus y minus cy prime. Y prime is going to be the velocity of this object, and this will be equal to my double prime. Now, a moment ago, we've determined that when we're at rest, we can swap out L for mg over k. So when we do that, what's going to end up happening, if you substitute everything in, these first two terms will cancel out. We'll get a negative ky minus cy prime is my double prime. And I'm hoping that at this point you can see that we end up with a model for this function y of t. It's a second order constant coefficient problem. So we are going to say that all of these constants m, c, and k can be greater than or equal to 0. So there's the mass. We'll have that in units of kilograms. This is the air resistance coefficient. This will turn out to be in units of kilograms per second. And this thing k will be the spring constant. And the spring constant is a number. The bigger the number, the stronger the spring is, the stronger that spring force. And this is indeed a second order linear constant coefficient dE. Now, another name for this air resistance sometimes is called a damping constant. In what's called the undamped case, damping means that there's some sort of external resistance due to the medium you're in. So air resistance, or perhaps if you're in water or honey or something like this. So there, in this case, there would be no air resistance. Now, unless you are in a vacuum, that condition isn't very realistic. But nonetheless, it's a good place to start because it helps us build up the sophistication of our model. Now, this is a basic constant coefficient problem we've studied before. We know that this has solutions e to the lambda t. Generally, we like to put this in an initial value problem. So let's say y of 0 is y naught and y prime of 0 is v naught. So this is the initial position and this is the initial velocity. We're going to get a characteristic equation. M lambda squared plus k is 0. So lambda squared plus k over m is 0. And you know very easily that you can solve this. And what you'll end up getting is lambda is square root k over m I. It has imaginary solutions. For convenience, we are going to call this thing omega naught. So it's not a W, it's an omega naught. And we're going to say that this is the natural angular frequency. And we'll talk about why that is in just a moment. Now, given that we have complex solutions, the general solution to this problem, we already know the basis functions. The basis functions here are going to be cosine of square root k over mt plus sine square root k over mt. We could write everything here in terms of that natural frequency, omega naught t, and same thing in the other case. Now, as a specific example, we've got a system where the mass is equal to 1. The spring constant is 5 newtons per meter, which is the more common units. We'll have the initial position is a 1, and the initial velocity is 5. So someone's held the spring downward and then given it a downward velocity. So in this case, the initial value problem that we're going to solve is y double prime plus 5y is 0, y of 0 is 1, y prime of 0 is 5. We know that in this particular case, we are going to get a very quick answer, cosine root 5t plus sine root 5t. We want to apply the initial conditions. And to do that, we're going to need the derivative, negative root 5a sine of root 5t, root 5b cos of root 5t. And if we apply the initial conditions, we'll get a is equal to 1. And if we apply the other one, we'll get negative root 5 times 1 with a 0 plus root 5b is equal to 5. So that means b is going to be root 5 again. Now, the particular solution will then simply be cosine of root 5t plus root 5 sine of root 5t. Now, by this stage of the course, we're all pretty good at getting formulas, but we want to be able to say something about this, right? What should I see? So to try to help us understand the behavior, we're going to take a look at this and say, look, when I see two coses or sines and they've got different coefficients in front of them, I'm going to remember, even though I really won't, that there's a trig identity that allows me to write functions in this way. And that trig identity is the following. Cosine of alpha minus beta is cosine of alpha times cosine of beta plus sine of alpha sine of beta. Now I'm going to compare here. It's up to me to choose which I'd like to be alpha and which I'd like to be beta. It doesn't really matter, but the most important thing I'm going to do now is I'm going to scale this by some constant, r, and I'm going to multiply everything here by that r. And then what I want to do is now take a look at what I've got and try to compare it. And I want to compare it to this. I want these two to be the same because I'm trying to figure out what this is in terms of a single cosine function. And I want this to be equal to some sort of r cos beta times cos alpha, r sine beta sine alpha. Remember, the order doesn't matter because they're all being multiplied, so it's kind of irrelevant. So I need these things to be true. What I need is two equations to help me find beta and r. Finding r's pretty straightforward. 1 squared plus root 5 squared is going to be r squared cos squared beta plus r squared sine squared beta. So that means r squared is going to be 6, so r is root 6. Beta is also pretty straightforward to find. I'm going to have that r sine beta over r cos beta 5 over 1. And that tells me that the r's cancel and the tangent of beta is root 5. So beta is going to be the inverse tan of root 5. Now, that's some strange number. It's about 1.15 radians. Why am I going through all of this? Because now I get to put this together. The solution, which was cos root 5 of t plus root 5 sine of root 5t, when I put this together, I can write this as the square root cosine of alpha minus beta. So that's root 5t minus the inverse tan of root 5. Now, these are some strange numbers, I fully admit. This should be a lot more familiar to you in terms of a picture. All right, it's a single cos function that's been shifted by some amount beta. That's what this phase shift is about. And its amplitude has been increased beyond this natural. And when I go ahead, I know that its initial position has to be 1. So if I go ahead and I do this, I'm going to figure out that I have a function, a cos function that just kind of does that. From peak to peak will be the period. And in general, the period here is always 2 pi over the natural frequency. So this is 2 pi over root 5, which is about 2.81 seconds, if you do the calculation there. And this is the point. For undamped motion, you can always write the solution as a single sinusoid. It could be a cosine, it could be a sine, it doesn't really matter. The natural frequency of this thing is K over M. And you can see that lots of different behavior happens, right? You can predict the behavior based on this frequency. So if the mass increases, if this bob gets heavier, right? If the mass increases, the frequency will decrease and the period will increase, right? So it will go slower. It will take longer. There's more work for the spring to do because the mass is heavier. If the mass decreases, the frequency will increase and then the period will decrease. If the mass is lighter, it will bounce around more quickly and it doesn't need as long to get back to where it was. Now, if your spring force increases, that means your frequency will increase and your period will decrease. You've got a tighter spring. It's stronger. It can restore more quickly. But if your K is smaller, your frequency will decrease, your period will increase. A weaker spring is very loose and it's slower to return. So in general, you will not really observe an undamped oscillator. This is kind of a perfect ideal situation. But once we understand that there are certain parameters in this model, so we say that these natural frequency, this is really the one thing that we care about in this model. It's a good warm-up for a more realistic case.